Hello again everyone, welcome back to ptet.chemistry channel. So to supplement what I covered on understanding chemical energetics previously in the other video, this video will entirely focus on calculations, how to utilize enthalpy changes of formation and combustions in working out enthalpy change of reaction. So this is actually a two-parter series on this particular concept, and this is the first part of that video in order to make each one not as long and as tedious as it seems to be. Okay, so I'm going to start off by just thinking very briefly about reactants going to products. Okay, so it has an enthalpy change of reaction. That's what you want to find. And then we can think about the elements. When the reactant is formed from the elements and when the product is formed from the element. Okay, we can have the formation of the product, but then we could have multiple products, so we are going to sum up. We're going to sum up the formation of the product, for which formation is defined for forming 1 mole of the product. So I have to multiply by however many mole of each product I have, and I have to sum up their individual enthalpy of formation. Okay, the same thing there. The reactants are formed from the element, so it is the formation of the reactant. But I could have more than one reactants. Okay, so I need to sum up their enthalpy change of formation of the reactant. I hope you can see the Hess cycle going from reactant to products. Hess' law says that the enthalpy change of a reaction is independent, meaning it does not depend on which route you take, whether you go directly or whether you go via this particular route. When you go via this particular route, you have to go opposite this, and then you add that. But this direction are defined by these particular enthalpy changes, as you know by definition. So meaning to say the enthalpy change of reaction, when you go opposite, is going to be minus that plus that. Okay, so it's minus the enthalpy formation of reactant plus the sum of the enthalpy change of product. A lot of people, they will not be familiar with this. Instead, they often remember the mantra, product minus reactant, product minus reactant. But then you need to know what exactly of the product. So we're talking about the sum of the formation of the product minus the sum of the formation of the reactant. I've just rewritten it so that I get the positive term in front and the negative term as a second expression, because this is the Hess cycle. It all comes down to the Hess law, as well as what do you know about the definition for each of them. Okay, so this thing is the capital sigma in Greek letter. I don't think I've written it as well as I could. It means the sum, because you get multiple product, you get multiple reactants. And formation is defined for forming 1 mole of substance, which means you need to multiply by the correct number of moles of the substance in the balance equation. That's why balance equations are very important. Okay, so if you are given the enthalpy changes of formation in the question, you can work out the enthalpy change of reaction by taking the difference of the sum of the formation of product minus the sum of the formation of the reactants. Okay, and that reaction could be any reaction. Typically, that reaction will be a combustion reaction, which seems quite counterintuitive, right? If it is a combustion reaction, but they give you this data, you still use the same expression. I'll show you what I mean. I'll probably start off by drawing a Hess cycle for each one, but then eventually at some point I will stop doing that unless I'm specifically being asked by the question. Yeah. So here, this is not a combustion question. So in this first example, I'm given the formation data. Okay, keep in mind that the definition of the enthalpy of formation defines the enthalpy change for forming 1 mole of the substance. Okay, etc., etc., of course. So what is the enthalpy change of this reaction? All right, what do they give me? Bear in mind that this is an element, and in the other video, I talk about the formation of an element from its element in under standard condition. By default is going to be 0. That's why you see they only give you 3 data without this data. Okay, so you don't go away and do bond energy or whatever, because that doesn't make sense. We are working along this domain of enthalpy change of formation. Yeah, so the enthalpy change of reactions is the sum of the enthalpy change of formation of the product minus the sum of the enthalpy change of formation of the reactants. So the use of bracket and multiples are very, very important. I know the nitrogen by default is 0 because it's the formation of an element. I've got 4 H2O gas there, okay? So they specify that it's a gas, and I'm forming 4 mole of it. That's why I need to multiply by 4, because this is, by definition, for forming 1 mole of it. Okay, so again, it all comes down to, do you really know the definition, or are you just remembering the definition without knowing what it actually means? Okay, I think I've done it wrong. N2H4, there are 2. Oh yeah, that's fine. And then N2O4, there's 1 of them. All of them is in kilojoule per mole. I've used 2 big square brackets to separate the 2 terms, because as with any calculation, it's important to not make any mistake, and this will make it much easier to check, especially with the use of bracket. All right, so minus 967.2 minus 110.4, I will get minus 1077.6 kilojoule per mole. If this is a theory paper, the maximum given there is 4 sig fig, there's 3 sig fig, there's 2 sig fig. I would probably be safe if I convert it to 3 sig fig or 4 sig fig. I'm going to convert it to 4 sig fig there, but I'm sure 3 sig fig would have been alright. 2 sig fig would have been too little, I guess. Alright. Anyway, the important here is not the significant figure, but rather the strategy involved in the calculation. Yeah. So this is again another straightforward question. Alright, so I'll just get on with it. So I know it seemed tedious to write down that formula, and it's not exactly a formula, right? Like, I mean, I started this tutorial video by going through that reactant to products general reaction scheme, and then you could see how I get it. It doesn't appear by magic. It appears with the application of Hess law, as well as the idea that enthalpy change is like a vector quantity, so its direction matters. Yeah, so 4 times the product of the formation of the product, which is minus 1279. Okay, and then for the reactant, I have 1 of the P4O10. I have 6 of the H2O liquid. A lot of these calculations comes down to bookkeeping. Can you be neat enough in your handwriting, and can you make the life easy enough for the examiner to work through your working, and also for you to read back your own working. Like here, without the use of bracket, you might easily make a mistake already, whereas when you use a bracket exactly and do it step by step, you minimize that risk. Okay, some people, they just like to put in everything into calculator, which is fine when you get it correct, but the question is, what if something bad happened? What if you mistakenly key in 1 extra number or forgot something? Okay, that's why you need to check. That's why it's important to write it out so that it's nice and clear. Yeah. Here they give you the enthalpy change of combustion. So really speaking, again, I should probably have a separate slide. Let me just work through this. If I add in a page, okay, so I can add in this page here. Why is this one here? Okay, I don't know why I can't erase it, but that is so weird. That is just really weird. Anyway, so you have reactants and you have product, and you want to find enthalpy change of reaction. So this is similar to what I have before when I first derived the expression using the enthalpy change of formation. But here I will use the enthalpy change of combustion. So I have to think about combustion products, no longer the elements, because I'm talking about the enthalpy of combustion of the reactants, from the reactants to the combustion product. But I could be burning more than 1 mole of the substance in excess oxygen, so I need to sum up the combustion enthalpy. I need to multiply by the correct mole in the equation, and this is the sum. This is the sum of the enthalpy of combustion of the product. And I hope you can see with the use of Hess cycle again, delta HR is the sum of the enthalpy of combustion of the reactants minus the sum of the enthalpy of combustion of the products. Here we're going the natural direction, but here we're going the opposite direction, so it has to be minus that. Okay, so this is using if you are given the enthalpy of combustion, then you can work out the enthalpy of reaction. And I can tell you, this one sometimes the reaction is the formation. So it seems counterintuitive to use the combustion enthalpy to work out the enthalpy change of formation. But it all comes down to this fundamental concept. Okay, do you know that you can create a Hess cycle? And do you know you can get a relationship between them? Alright, just by definition alone. Anyway, so if you're given the enthalpy of combustion, so this is the enthalpy of combustion of methanol, the enthalpy of combustion of H2, enthalpy of combustion of carbon there, and you want the enthalpy change of formation of methanol. Okay, so maybe with this case I can write an equation. I want the enthalpy change of methanol, formation of methanol, form from its element. So writing balance equation first of all. So methanol is a liquid at room temperature and pressure. I have 4 hydrogen atoms altogether, so I need 2 of the H2 and I need half of that. Okay, so I want to find the enthalpy change of reaction, but I'm given the combustion. So I have the combustion of carbon, yes, because that's given there. I have the combustion of hydrogen, yes. I have the combustion of methanol, yes. But I do not have the enthalpy of combustion of oxygen. But in the other video, I already told you about this identity. What does the combustion of oxygen means? The combustion of oxygen means burning 1 mole of oxygen in excess oxygen. And oxygen itself is not flammable. Oxygen support combustion, but oxygen itself is not flammable. Oxygen does not spontaneously light on fire. If that is the case, you are breathing in oxygen at the moment, you would be breathing in fire instead, yeah? So you need to think very logically. So maybe I don't want that. So the enthalpy change of reaction is the sum of the enthalpy change of combustion of reactant minus the sum of the enthalpy change of combustion of the product. It's not very clear without writing this equation what you have, what you are expected to find, yeah? So you really need to write down this equation, otherwise you will get the wrong multiple just by looking at this, alright? And it doesn't work like that unless you have a balanced equation for the reaction that you want to find. This reaction happens to be the enthalpy change of formation, as I mentioned previously, yeah? Seems counterintuitive, but we know that by definition this is whatever it is, yeah? So the reactants are on the left, 2 at 6, and then minus the combustion of the product. I have 1 of the methanol. So right now I'll space there, but anyway, it's minus 966, it's minus 726. So the use of bracket again there, I hope you can see the minus become a plus, and sometimes you mistakenly omit that step when you just put everything into a calculator, and that is quite bad, yeah? So with everything I've shown so far is exothermic, but your calculator will not show you the sign if it is endothermic. It's very important when we talk about enthalpy change that you have a sign, you have a value, and you have a unit. Whether it's plus or minus, you've got to show it, okay? Next bit, they give you the equation. You see, this is the reaction. The reaction happens to be the formation. So the enthalpy change of reaction, which is equal to the enthalpy change of formation of butane, but I'm focusing on the enthalpy change of reaction given enthalpy change of combustion, is going to be the sum of the combustion of reactants minus the sum of the combustion of the products. So you gotta keep an eye out for what is what. That's what my point is really. Okay. So that is going to be your reactants there. So there's 4 carbon. You need to multiply by the correct number of mole, because by definition this is combusting 1 mole of the substance. Here you have the combust 4 mole of the substance. Alright, that's why you need to get the correct multiple from a balanced a balanced equation. That is very, very important. Yeah. So again, 2 at 7, 7. So there's a negative there. So altogether I get minus 129 kilojoule per mole. All right. Okay, question 5. It's getting more and more complicated now. What do we know? So we're given a mixture of formation and combustion, right? But this is what we want. So we want the formation of CS2. It seems like I'm given 3 values that have formation. So this is what I want to find, but I have more of the formation than this, meaning to say I could be looking at this reaction. And then I use this data to work out the enthalpy change of this reaction. So this is what I think when I see this kind of question. Yeah? So if this is the reaction I want to see, so there's combusting 1 mole of the substance, that will give me that, and that will give me SO2. The reason why I think it's SO2 is because they give me SO2 there, so I should be forming SO2. The carbon are balanced, the sulfur are not balanced. Alright, so the sulfur is now balanced, the oxygen are not balanced. So there's 2 oxygen, there's 4 oxygen, so I need 6 oxygen, there's 3 oxygen. I will assume that this is in the standard state as that. I don't want to confuse you with the standard state here. But what do I have? So this is the enthalpy change of reaction, which so happen to be the combustion of CS2, which is minus 1110. You're burning 1 mole of the substance. Alright, happy? But at the same time, we have the formation value. The formation value of CS2 is what you want to find. So let that be X. That is what you want to find. Formation of oxygen is 0 because you're forming the element from its element. So you know the formation of elements like oxygen or hydrogen or nitrogen or whatever elements is going to be 0. The formation of CO2 is minus 395. The SO2 is minus 298. But bear in mind that the enthalpy of formation is defined as for 1 mole of the substance, to form 1 mole of the substance. Here you form 2 mole of the substance. So when you do your calculation, so the delta HR, which is minus 1110, which so happen to be the combustion of CS2 based on this equation, is going to be the sum of the enthalpy of formation of product minus the sum of the enthalpy of formation of reactant. And I can only work it out simply because I know the data there mostly is delta H formation, and therefore I started by writing this equation that represents the combustion. Okay, so the formation of the product is going to be minus 395 times 1 for the CO2, minus 298 times 2 for the SO2, minus X times 1. Well, there's only one CS2, so it's X times 1. Okay, I hope you can see then, if I move this minus X to the other side, then I'll get plus X. I'll move this to the other side, I'll get plus 1110. And then I'll get whatever is in the bracket, the first bracket there, minus 395 times 1, plus 2 times minus 298. I get minus 991. And that gives me X as, your calculator does not show you this, but this comes down to how skillful are you at understanding sign value unit, enthalpy change, sign value unit. You forget this, then you don't really know what is enthalpy then. Okay, so that's the end of this first part of the video. I'll stop it there, and I'll see you in the second part of this video where I do more advanced calculations on these values involving enthalpy changes of formation and combustion. Okay, so if you haven't subscribed to the channel, please subscribe to get notified of future updates and more great content. I also look forward to hearing from you guys, the students, as to what kind of concepts, what kind of questions are difficult to you. Then I can think about making more tutorial videos on those in the future. All right, thank you for watching.